My name is Paul Vercellotti, software architect at Avid Audio, where I work on Pro Tools and other audio products there. And today we'll be exploring first the impact of latency on the professional musician, and how to work with musicians' latency needs when creating audio processing systems. So we'll be looking at the architecture and design of how to build systems that do low latency audio processing, and how where that intersects with human perception of latency, and how these two impact system design. Probably the audience would be most interested might be plugin developers who haven't explored so much the systems aspect of this, or had a chance to get their feet wet in DSP or embedded development, and are curious about what goes into that. At Avid Audio, we spend a lot of time thinking about those problems for both our Pro Tools systems as well as our live sound systems, where every bit of latency makes a lot of difference to the musicians who are performing. So the basic problem is that in live performance, on stage as well as in the studio for recording, musicians need to hear themselves in the mix as they play, and they need that with a minimum delay, latency between when they play the note and when they hear it. And they want to hear that in the mix with processing applied. So how much latency is acceptable? There's a gap of what's acceptable and the musician can compensate for, and then what is ideal, where the musician doesn't think about it. There's no cognitive dissonance from playing to hearing that they have to spend mental energy on. And when that latency goes away, the musician can just focus on their performance. They can just drop right in, and it's not something they're having to spend any attention on. It turns out that the gap between what's tolerable versus where it just disappears for musicians makes a big difference in the design of the system. The entire architecture changes as we go from either desktop systems, embedded or DSP, and the hoops you need to jump through to deliver the low latency that musicians want become increasingly challenging. So we'd like to explore that a little bit. Let's start with a little exploration into how musicians perceive latency. So there's been a lot of studies around when can musicians hear it, when does it impact them, and there's been more recent work on what are the maximum tolerable latencies, with everyone stuck at home, trying to collaborate, as some of the other presentations have explored. We've wanted to know what are the maximum latencies that we can adjust for and still have a good performance. But in a professional setting, recording studio, on stage with 50,000 people watching, we're interested in what's the minimum latency that we can achieve, and performers can get the best experience from. So, a 2007 study presented at the AES convention by Boley and Lester at Purdue University and Shure microphone company found with a variety of musicians playing both drums, guitar, saxophone, vocals, the tolerable latencies were in the high tens of milliseconds, milliseconds that they could compensate for. But when they really found the sweet spot, when the performance just dropped in for them, and their in-ear monitoring was no longer something that they noticed, they gave subjective ratings, and authors of the study had some interesting findings. So one of the interesting findings was that with different monitoring techniques, if speakers, monitoring through speakers versus head in-ear monitors. Microphone working all right? Okay. In-ear monitors versus speakers, the musicians had different tolerances for delay and what they could compensate for. They were willing to put up with a little bit more from speakers because, of course, audio sound travels through space around 3 milliseconds a meter. So there's going to be some latency intrinsic to that. But they found that musicians doing in-ear monitors had much less tolerance, especially musicians who play instruments with sharp attacks, especially when they're trying to play in time with a metronome or a click track. And professional drummers were the most demanding in terms of when they felt their performance was just thrown off by the latency that came in. So let's look at these times. The times are very small. Probably the worst case for the professional drummer, less than a millisecond they could perceive, and they felt it threw off their performance. Now, those very small times, human ear can't perceive, the differences between separate events. One theory for why that happens, that it does throw them off, is filtering, comb filtering effects that happen between, the acoustic signal as they hear it, and when the audio from the monitors interferes with those two. So very small tolerances there. At the other end of the spectrum, keyboard players had the most flexibility, and they are used to compensating, especially with, because they're used to playing with sounds with long attacks, strings that, take a while to build, and it's a little bit in the keyboardist lexicon to play a little bit early. So thinking in terms of how we design a system to accommodate this, if we want, sub-millisecond or sub-2 millisecond latency in a system, how do we achieve that? First, let's take a little bit to explore what goes into this latency and why it happens. So this is a theoretical audio processing system. They'll all have these components. This could be a dedicated mixing console at a stage with audio processing. This could be digital audio workstation connected to your audio interface that are running your plugins. Either of these could be settings where you want to do the audio processing that you develop for, and the latency involved in that impacts the musician. Okay, so just a quick overview. We'll go fast through these. We've got just the distance to the microphone. That alone can introduce a piece of it. The analog to digital conversion. The converters themselves impart a small amount of latency in order to do things like compensate for clock jitter and things like that. Keep the sound quality as high as it can. Frequently, audio interfaces have internal routing that add another layer of it. But the biggest area that I'm sure we're all familiar with is the buffering on input and output. In addition to the processing itself, that's where we've got the most levers of control to compensate for this. Again, the process is symmetrical on the path back to the monitor. So each one of these adds a little bit of latency, and there's a certain amount of fixed overhead that we're not going to be able to do much about. We convert from analog to digital so that we can do digital processing. and apply the cool effects that we're excited about. The internal routing and all of that are just intrinsic to building a system like this, but the place where we can control it is the buffering. So let's have a review of just why it's difficult to bring that buffering down, and why we're up against the limits of both microprocessor design as well as operating systems when we're building a system that can do this. Here's a quick refresher on actual times in terms of buffer sizes and practical latency, minimum latencies that are encountered with doing a circuit, in this case from an audio interface to a desktop PC and back. We'll see that practical lower limits for a desktop computer are about 32 samples. If you take into account the round trips, the extra overhead, that's a minimum of 4 milliseconds of round trip latency that we can offer to the musician, and that doesn't take into account the intrinsic latency in certain audio processes like filters that have intrinsic delay in their processing. So this is the starting point. If we want to get the musicians the lowest latency possible, minimizing that buffer size is the best we can do. So let's take a little further about why we buffer in these quantities. So first, of course, the CPU, the microprocessors, whether general purpose or dedicated purpose-built DSPs, they do things better in large quantities. They perform better in loops. If you've optimized a plugin, you will have encountered this. Long loops, the same work. Processors do really well. Lots of context switching throws the processor off. It's got it blows its cache. It stalls the pipelines. It loses efficiency in all respects. Another aspect in there are the actual audio transfers when you're transferring the audio from the interface to the memory. Those tend to work better in large blocks. But even still, most processors, whether general purpose or DSP, can do a good job with audio processing at low latencies. The real trouble where we bump into are the operating systems themselves. So we've got different classes of operating systems. Of course, our desktop OSs, Mac OS, Windows, and Linux, have a lot of duties they're trying to perform, a lot of needs they're trying to balance. And jack of all trades, master of none, they have some lower limits for how fast they can get to our audio requests. As most people know, there are lower limits to your buffer size if you're working on desktop systems. Alternatives for that, if you're designing an audio processing system, of course, an RTOS, real-time OS, of which there are quite a variety. These attempt to simplify the problems if you've got a purpose-built machine and minimize the distractions that the OS is trying to achieve, as well as the minimum wake-up time to service a request. So as the audio buffers come in and out, RTOS can service them more quickly. And of course, if you want the best performance, just throw out the OS entirely, write all the software yourself, and you can absolutely guarantee the performance in that case. Let's explore a few of these. All right. Well, what are the steps with general purpose OS, and why do they have such trouble with really low latency processing? Let's explore the pieces that are happening. So general purpose OS is in order to have better stability, separate processing into kernel space and user space. As audio is delivered from an external device, this could be, a built-in. This could be an audio interface connected to a desktop system, or it could be a built-in audio peripheral on an embedded system. Either of these will interrupt the processor. It'll save context of where it is, and eventually service the interrupt and know that audio is available. Audio is being delivered back and forth. The audio interrupt handler needs to tell the kernel, hey, we've got new audio. Tell our user space audio thread, which is where normal software runs, to wake up. It might be completely high priority, but the OS itself is going to get in the way and take care of all of its different competing needs. And eventually the scheduler will come around after some variable amount of time and wake up our audio processing thread. That gap between the audio interrupt, when it actually gets serviced, and when the scheduler can wake up the audio processing, takes a lot of time. And the gap between those two can make quite a difference in how much CPU usage or utilization we get. So even though we have a really powerful processor, we might only have a fraction of the time of the audio period due to the OS preventing us. Let's take a step through of what those look like. So here's audio coming in regular intervals. We've sliced it into these buffers that we want to explore. Interrupt comes in on the buffer boundary, signals to the kernel that our buffer is ready to process. The kernel lets the scheduler know that the next time through it should wake up the audio thread, but the scheduler itself is triggered by its own interrupt, the OS primary interrupt, which is often delivered by a high frequency timer. That interrupt comes in, wakes up the scheduler. The scheduler sees that it's time to process audio, wakes up the user mode thread and jumps into it. You can see the gap there of, we've used up a lot of time waiting for that scheduler to wake up. And the more difficult part is that the time to wake up that thread is variable. We don't know how much it is. Different OSs try to improve that by providing better synchronization, ways of waking up or sleeping the threads. And they only leave a small amount of time for jitter. Apple's done a great job of improving that. But even with all those improvements, there's still jitter in these wake-up times, and you don't want to have a mission-critical audio processing system that has that variability. If you've got a concert with 50,000 people watching, and you miss your deadline, you've got terrible noise going out over the mains to 50,000 people, and it doesn't look good for the sound guy or the board that is making the noise. Let's look at some alternatives. If you take away the OS, we've got fewer steps in between. You can achieve much smaller buffer sizes by having a higher interrupt frequency, and there's no trouble with waking up the OS. This is what Avid audio products do for our DSP products in HDX, Pro Tools HDX, and our live systems. And it's a lot of work. It's more challenging to develop for, but at the same time, the stability and responsiveness are totally worth it. Different techniques that happen. We have different process chaining. The technique that you use for these different techniques achieve different CPU utilization. With the bare metal approach or very small buffer sizes, you can add latency and get better parallelization across systems, across CPUs. If you use larger buffer sizes, you might have multiple cores, but you need to, because of the funnel-shaped nature of a audio mixer, there tends to be less utilization as you mix down your submixes and apply your effects on your main outputs. So I'll throw in 2 plugs. Check out the Avid Carbon at the Avid table downstairs. This is our preferred platform for AX DSP. If you want to get your feet wet in that, we're going to be giving one of these away tonight at the ADC quiz night. So everyone show up for that.
For the open mic, actually.
Ah, okay.
Yeah, but there is similar prizes for the quiz.
There you have it. So at the open mic tonight, and similar prizes at the quiz.
So if anyone's in the forums who wants to do lightning talk, you can walk away with that.
Yeah. So show up for the open mic. I'll mention Avid Audio is hiring software developers, so inquire within, and we've got some time for questions.
Hi, do you ever use real-time operating systems in your embedded systems?
Yes, in our live sound system, we use real-time operating systems. So we use a combination of bare metal DSP processing as well as real-time OSs in our live sound engines. And the performance there, you can take advantage of general purpose processors, but get the guaranteed stability that you don't have with general purpose OSs.
Do you use the real-time OSs or when you're using embedded platform, do you use...
Could speak into the mic a bit more.
Oh, sorry. My question was, so you're saying you're using both the embedded barebone processing and with the RTOSs. So I'm wondering if you're using RTOS on embedded platforms or whether you're just using barebone C, for instance.
We use bare bones on our DSP platform that powers both our HDX system as well as our live sound plugins. That's the AAX DSP platform. So if you develop for AAX DSP, you'll be targeting the TI DSPs that we use on both of those, and you can deploy your plugins both on Pro Tools systems in the studio as well as venue live sound systems for live performance. The RTOS that we use is for the primary mixing engine for the live sound systems, which mix hundreds of channels and use we use Intel Xeon processors for those. So general purpose CPUs, but used in a real-time context to get a balance of power plus responsiveness.
If you were going to build a small real-time audio processing system, which real-time operating system would you choose?
That's a good question. There are a variety of real-time operating systems out there. A popular one, there's a real-time, the Preempt RT patch for Linux is an alternative build of Linux that improves responsiveness by reducing the number of locks in the kernel. A big piece of the puzzle, it touched on briefly on one of the slides, is when your audio arrives, you've got a signal to the kernel that you're ready to go. The kernel might be working on other things and holds off interrupt processing for a while, can lock these critical sections, big areas of code that prevent running. Preempt RT helps with that. There are many wonderful RTOSs out there, though, that help with that. A long one running QNX runs well. VXWorks is used in many other industries. There's FreeRTOS, which is an open source project that does really well. Provides just bare bones, minimal hardware abstraction. So while providing, the basic tools for memory allocation, threading, things like that.
But are there any of them that are particularly easy to get started with?
Let's see. If as a hobbyist, I can endorse the work by Elk Systems, who have a build of it's a build of Linux with the preempt RT patch, as well as their audio drivers and board support packages. That they've made a really nice package to help with that. You can develop with Juice. So a shout out to Elk Audio for building a really nice system to experiment with if you want to try things at home with hardware and embedded.
It's from online. Are you planning to use or already use FPGAs instead of DSPs for signal processing in your products?
It's a great question. If you want the lowest latency possible, and indeed, for many decades, digital hardware manufacturers used custom ASICs, custom chips, custom silicon to achieve really low latency. It's hard to build chips. You have to make a lot of them. It's complex engineering. It's hard to fix bugs. FPGAs are programmable hardware. They can achieve extremely low latencies and do single sample processing. We do employ FPGAs in many Avid audio products, both in our studio and live sound products. Those help with kind of the foundations of the audio, but it's hard to build plugins for FPGAs. And as the maintainer of a platform that we like third parties to develop for, FPGA development is deep and tricky. It's not exactly software. You're building circuits, digital circuits in code, and it's a different mindset. So in that regard, we're not likely to use FPGAs, but for purpose-built hardware, especially low latency mixing, they do a great job at achieving low latency.
When you're using say an x86 processor, as you mentioned, that's been sort of architecturally designed for throughput rather than for consistent latency, you're trying to get that lowest latency out of that processor possible, or the lowest jitter. Obviously, there's a lot of microarchitectural stuff that you can't control potentially, or is difficult to control, that is going to affect how long any given cycle is going to take to issue and retire. So is that something that you find on x86 or for commodity processors, as you say, compared to taking a DSP chip? Is that something you find you have to care about a lot, or is it so simple?
Absolutely. Those effects are one of the downsides of using commodity general purpose processors. One of the main appeals of purpose-built DSP processors is not so much that they run fast. That was the case a long time ago. Now, general purpose processors run plenty fast. But DSP processors offer predictability. You can guarantee how long your code is going to run, and it's fairly predictable. That is gold for a real-time developer. So those effects are huge, and in our own experience building systems with x86 processors, we have to leave a lot of room and compensation for effects like complex pipelines, code and data cache behaviors. If you service something else, you've lost your cache. A piece of code that took 10 microseconds to run a moment ago might take 30 microseconds. These are the kinds of things we think about as we try to balance those different needs. Yeah, thank you for the question.